So cobalt oxide is known to be an antiferromagnetic insulator. And we were trying to understand this in terms of whatever we have learned about band theory. And one of the things that we learned is that for some material to be an insulator, uh, you have to have an even number of electrons per unit cell in that compound. But if you do a valence electron count, cobalt oxide, for that, of course, you have to know what the structure is. And the structure happens to be a rock salt structure with one cobalt and one oxygen in the unit cell. So which gives you 9 plus 6, that is 15 electrons in the unit cell, which is, of course, an odd number. So therefore, it's a puzzle how you get an insulator. One could argue, we were trying to argue this way, that, well, after all, it's an antiferromagnet. So what is an antiferromagnet? Very simplistically looking at it, whatever the structure, if I draw it in 2D for simplicity, I have certain, and the magnetism, of course, comes from the spins on the cobalt atoms here. So it's a schematic. So alternate spins are up and down in some way. And there could be several types of antiferromagnetic ordering, but let's not worry about that. But so in an antiferromagnet, if I go to a site which has a majority up spin, then at least one of its neighbors would have majority down spin. So therefore, the unit cell, one can argue, is really double of what we were thinking, because we have to now include both the up and down spin cobalt atoms in our description of the structure. So the unit cell doubles up. So if it doubles up, then you have 30 electrons in the unit cell, not 15 anymore, and one could have an insulator. The problem with that is there are several problems. The first question is, if you do a band structure calculation, can you, with this doubling of the unit cell, do you get an antiferromagnetic insulator? We'll not get into that question. All that I said was that even the standard band structure theories find it difficult to describe such compounds. And today we'll understand why they find it difficult. But we give another argument, which is that suppose we are increasing the temperature. We start from very low temperatures and then we are increasing the temperature. So what happens? Now, these are things I assume you have learned in your statistical mechanics at some level. So I believe you are familiar with phase transition, etc., right? Have you done this in StatMech? Yes, no, Manojit?
Sir, we have done little bit, but not in detail.
No, little bit is enough in the sense that there are, temperature-driven phase transitions. Depending on the system, if you are lowering the temperature, then below a certain temperature, long-range order appears. If it's a ferromagnetic system, the long-range order, of course, is ferromagnetic. You could have antiferromagnetic long-range order. So are you familiar with this idea of long-range order and the fact that at low temperatures, these long-range orders appear? I mean, are you familiar with these ideas?
Not very much, sir.
Oh. Okay, let's see what we can do, maybe in the subsequent. But for now, let's just take my word that you start from a high temperature and you find that there is no magnetic order in the system. I'll try to make it more sort of concrete what we mean by an order. But as you lower the temperature, then at some temperature, this long range order appears. And that is what we call ferromagnetic. I mean, if the order is ferromagnetic, we call it ferromagnetic order. If it is antiferromagnetic, we call it antiferromagnetic order. So here we are talking about an antiferromagnetic order. So now in temperature, we are going the other way. When we are at low temperatures, there is an antiferromagnetic order in the system. Now, as I increase the temperature beyond a certain particular value of the temperature, the order disappears. There is no long range order anymore. So in that state, when there is no long range antiferromagnetic order, there is no doubling of the unit cell, okay? Because the spins are not ordered in any particular way. So therefore, that argument doesn't hold anymore. And but the system still remains an insulator. It becomes a paramagnet, but it's an insulator. So these ideas, ferromagnet, antiferromagnet, paramagnet, we'll come back to these ideas in later lectures. Here the point is that argument then breaks down. And so how do we describe such a system? I mean, why do we get an insulator which is so robust? I mean, when it's antiferromagnet, it's an insulator. When it's paramagnet, it remains an insulator. So, but the band theory tells me that it should be a metal. So what are we missing? And that's the crucial point for today's lecture. That the short answer is that we are missing something very, very important. So what are we missing? Let's look at that. Where are my notes? Just give me a second. Yeah, so what are we missing? That's the point, okay? What we are missing is, as I'll slowly explain, what we are missing is there's a strong Coulomb interaction whenever there are more than one electrons on the cobalt side. And that's an effect we are missing. Now, to illustrate that, rather than focusing on any particular material, let us go back to our model systems, okay? Suppose we have a time binding model in 2D, a time binding square lattice. I mean, so yeah, so we have this square lattice in 2D, and we describe that with the time binding model with the hopping matrix element T. We have studied this. So now I will write the Hamiltonian of this model in the second quantized notation, which is also very standard. If you are not familiar with that, I can give you notes, or I can ask Devraj to sort of explain to you where it comes from. But here I'll write down the Hamiltonian and explain what these terms mean, which is sort of quite transparent. Okay, so that's it. So what is this term? So this C and Ci sigma and Ci sigma dagger, these are electron creation and annihilation operators on the site I. And therefore, this is a number operator. So this is an operator for the number of electrons. This is the annihilation operator. This is the creation operator. Sigma is the spin index, which can be up or down. And I means one of these sides. So this, as you see, is just gives you the on-site energies. Okay. So let me write it as epsilon, not minus. So every site is equivalent, and there is an energy epsilon when an electron sits on that. And then this is our familiar hopping term. Now, what happens here is, for example, if I look at this term, there is an electron of some particular spin up or down on side J that is annihilated, and an electron of the same spin is created on the side I. So therefore, this basically hops one electron from side J to side I, and this is the other way around. And this symbol here means that we only allow nearest neighbor hopping. So only if I and J are nearest neighbors, this hopping matrix element is non-zero. Other hoppings are neglected. That may not be the case, but that's a simple approximation within which. So this is nearest neighbor type binding model. Okay. Right. And you can actually start from this model and do a Fourier transform to K space and get the exactly same dispersion relation that we derived from more sort of microscopic atomic picture earlier. So let's stick to this for the moment. Now, what happens when I have such a model and the electron tries to sort of, okay. Now, with this model, in fact, we have sort of looked at this question, at least in 1D, that when I have one, so my situation is that I have one electron per site. So we got a metallic system. If you remember, in one dimension, we got a band structure that looked like that, and half of this was occupied, half the states were occupied. So this part was occupied and this part was unoccupied. So therefore, we got a metal with a finite density of states at the Fermi energy. So this would be my Fermi energy. So I get a metal. If you go to 2D, you get exactly the same thing, except that your Brillouin zone now becomes two-dimensional. So instead of just one K direction, you will have two K directions. But you fix one, if you fix one of the Ks, if you fix K, Y, and draw a band structure along Kx direction, you will get exactly the same band structure. And with one electron per site, you will get a metallic system, half-filled band metallic system. Now suppose on such a lattice, an electron is trying to move around. What will happen? So to start with, I have one electron per site. Okay, I don't bother about the spin right now. I'll come back to the issue of spin later. So now suppose this one tries to go here. So when it goes here, it occupies this site. There are two electrons on the same site, and I have taken one orbital per site. Okay, so I have one orbital, one electron per site. So when I say the system is metallic, the electron can conduct current. I have a partially filled band. So this conduction involves hopping of these electrons, and whenever electrons hop, there has to be two electrons on the same site, on the same orbital. And whenever that happens, remember our discussion in the last lecture, two electrons occupying the same atomic orbital costs you energy, okay, which we introduced as this quantity U. So here, if phi is the orbital, whenever two electrons are on the same orbital, it will cost me this much of energy. So this is the effect that we have been neglecting so far. Okay, half-filled band metal, all fine. But whenever there is an electron motion, two electrons have to be on the same side, and that costs energy. So the question now is, suppose we introduce this effect in my Hamiltonian. What happens then? So I augment my Hamiltonian with this term. So how do I write it? So now I'll erase this part. This we have seen earlier. So I'm introducing this additional term here. So you notice this is just in and down the number operator, and this is the number operator for upspin on the side R. So that will take care of this on-site electron-electron interaction. This term is the usual Hubbard term. We have encountered this when we consider ionic configurations of H2 molecule. And this Hamiltonian, now the type binding plus this U term is called, so this whole thing is the so-called Hubbard model. So this Hamiltonian is the Hubbard Hamiltonian. Type binding plus on-site Coulomb interaction. This model is called the Hubbard model. Now notice that we have defined this Hubbard model in some restricted sense here, in the sense that I have taken only one orbital per site. So here I have one orbital per site. And okay, so that's the first thing. So this particular case is called the one band, which is sort of a misnomer. Better nomenclature is sort of one orbital Hubbard model, but it's routinely called the one band Hubbard model. And although it need not be at all, but in the discussion that we were having, we said we have a half-filled band, one electron per site. So when I have on such a model, when I have one electron per site, that's a very special case. In fact, what I can do is, say I have L sites in the lattice or in the crystal, whatever, and if I have n electrons, okay, then the small n is called the filling of the model. If I have L sites with one orbital per site, I can have a total of 2L electrons. But then if n is equal to, if I have one electron per site, so the maximum of n I can have is twice n. If n is equal to L, that is one electron per site, then small n equal to 1. So this small n equal to 1 case is called half-fill, because you have half the maximum number of electrons you can have. So that is simple. This is just some nomenclature. But here is the model. And it need not be at half filling. But half filling is a special and interesting case. And there are situations, there are materials which are like half-filled Hubbard model, which can be described by half-filled Hubbard model. So see. Okay. So what is the effect of U on this electron motion? Let us look at, we have already looked at one limit. When U equal to 0, I get a vector. Because they can freely roam around. In fact, they gain energy, which goes as T as they move around. Let us look at the other limit. So, if I have to write down U equal to 0, I get a method. In fact, it's a paramagnetic. Let us look at this limit. What happens in this case? Oyon, what do you expect? I don't see a. Anybody? Sayan, what do you expect?
Sir, you are asking when
You
it goes to infinity, what will happen to Fermi level or what?
No, I'm asking what happens to the electron motion when U goes to infinity, that limit.
where does it go to infinity?
No. What? It's not. See, it's the same U on all orbitals. Okay, all orbitals.
All
are
the
the same.
Okay, so then only that interaction will matter, and all the
electrons
other.
will clutter in nearby sites or independent site, but they will be up and down at each site.
Can you repeat that answer, Aman?
Sir, if the electrons are like all are spin up, but at each side, but then they will come and occupy sites. N sites will be empty, but the half of the sites. I mean, if there are n sites, then n by 2 will be occupied, n by 2 will be empty, and the n by 2 sites each will have 2 electrons, but one up and one down.
Yeah, but I'm talking of the U going to infinity limit. So if you put 2 electrons on
Electrons
each
will
side,
clutter up.
huh?
They will try to, I don't know, they will try to come nearby, localize. They'll.
But that's not the meaning of localization.
I think that the metal will not accept any other electron. Something
No,
like
there
that.
is no question of accepting any other electron. I mean, number of electrons is fixed. Okay, number of electrons is fixed. My question is, on an average, you have 1 electron per site. Okay. Now, we are looking at a material. So, of course, this what the value of U is differs from material to material. Given a material, you have a certain value of U. Now, suppose we are thinking we have a material on which U is very large, which mathematically I can take as U going to infinity. Okay. So in that limit, what we saw is that when U is equal to 0, when U can be completely neglected, can you hear me?
Yes, sir. We
Yes.
can.
There was some disruption, someone else logged in. Anyway, so what I'm saying is when U equal to 0, it's our usual half-field tight binding model,
which is a metal, because I have a half filled band. And when I say metal, I have a finite density of states at the Fermi energy. And it also means that electrons can carry current, which means that they can hop around the entire sort of extent of the lattice easily. My question is, what happens to that picture, that electrons hopping around without hindrance, when U is very large in some other material? What happens there?
Maybe the hopping will
Hopping will not happen because that term is
No, hopping will
overshadowed.
dominate because that lowers the Hamiltonian.
Okay, so two different answers. I think both are correct in two different limits. So let me explain that. So when U equal to 0, that's when obviously the hopping dominates. There is nothing else except for that on-site energy. But that on-site energy being the same on every side can simply be neglected. And I can set that as my 0 of energy. That doesn't change any physics. So only term that I have in the Hamiltonian in that case is the hopping term. That's the tight binding model we have studied earlier. Now I have introduced this U. So, and I'm talking of the extreme limit when U is very large. Then of course, the moment an electron tries to move, when it goes to the next side, there's already another electron. So that will cost a very high energy, okay, U. And U going to infinity, that process will be suppressed. So you won't have electrons moving around. So the system should become non-conducting. And in fact, that's what happens. Okay, so this phenomenon in which the electron motion is suppressed because you have strong intra-site electron-electron repulsion. This is called Mott transition. And these insulators are called Mott insulators. So let us try to look at it a little in a little more slightly more quantitative way. But none of these will be exact theory, because exact theory of any of these is way beyond what we can do in this course. But I'm trying to give you a flavor of the sort of physics that comes about. And what I want to, in the end, show you is that, again, there are many interesting sort of physics happening in these sort of materials, all of which are consequences of electron-electron interactions. And magnetism is just one of those. And sometimes it's not even the most sort of important thing happening, but it's happening along with other things. Okay.
Sir,
All right. Yeah.
on the microscopic level, what might cause the U to be very high?
Let's see. Different atomic orbitals have different shapes and sizes, right?
Yeah.
So if some of the orbitals happen to be sort of confined more closer to the in a smaller region of space, and then you put two electrons in such an orbital, that will cost you more energy. And the kind of physics we have in mind is, I'll mention a few. I've already mentioned cobalt oxide. There are other particularly 3D transition metal oxide materials, which are such that these are oxides. So there's an ionic bonding between the metal atom and the oxygen atom. So the metal atom has given up 1 or 2 or 3 electrons. So it is already in some plus charge state. It's a cation. So the remaining electrons will be even more tightly bound towards the nucleus. So they will be confined to a smaller region. So 3D orbitals are already small. And then on top of that, because it's in a plus something charge state, they are confined to even smaller region. They are more tightly pulled towards the nucleus. So these electrons will feel each other very strongly. So in fact, these are the kind of compounds where these sort of correlation physics becomes very, very important. And materials that, a naive electron count for which a naive electron count tells you that they should be metals, turn out to be insulators. And not just insulators, but they turn out to be magnetic insulators at low temperatures. And we are trying to understand both. Why do they become insulators? And along with that, why do they become magnetic? Okay, so why are we taking that limit? U going to infinity. So what is U? Now, what is U, as I said, is of course depends on which metal atom one is talking about, and which compound and so on. But typical values are several EV. Okay, 3, 4, 5 EV, it can go up to 10 EV, depending on which transition metal one is talking about. We are typically talking of transition metal d orbitals. T's, on the other hand, is EV or fraction of an EV. So in these sort of materials, U is several times, at least an order of magnitude larger than T. It can be an order of magnitude larger than T. So in such cases, the effect of U is very significant. All right. And so when U goes to infinity in that limit, of course, hopping is completely suppressed. But that's an extreme limit. Let us ask the question, when U is finite, what happens when U is finite but considerably larger than T?
So first, let us forget about the U term. When we had this as our type binding Hamiltonian, we have this sort of a situation. Again, these states are occupied, these states are unoccupied. We know the energies of these states because we know what the so this is the dispersion relation for this type binding model. And we can easily evaluate. So if half of these are filled, so from k equal to 0 to this is in 1D, pi over a. So this would be pi over 2a, and here it would be minus pi over 2a. So these states are filled, and these states are empty. So I can easily evaluate what the band energy of this is. And this will turn out to be something which is proportional to T. So if I call that energy E band, then the band energy in this sort of half-filled scenario is some number alpha times T. Let's not worry about what alpha is. I mean, you can easily figure out how to evaluate alpha, but that's not the important point of this argument. So this is the band energy when I have a half-filled type binding model. And then on top of that, now I introduce this U term in the Hubbard model. So what happens? Okay, I can write this as L. So well, L is the sites in the lattice. Okay. For the entire lattice, I can write it like this. Now, so this H interaction, what did I write it as? H interaction because of, or HU, no, let me write it. Oh, so E interaction, interaction energy, because of this U term. Now, let's not get into how to evaluate this, but I'll just write the sort of answer for you. One can show that if on a lattice which has L sites, the answer would be L2 over 4. So the energy, what do I do? It is this. So I'm going here. So the energy per site, which is E band plus E interaction by L, will be minus E for E plus E by 4. Now, when U is small, U is 0, U is small, this term will dominate. But as U starts increasing, this will become larger and larger. And there is a critical value of U by T. When U by t becomes what? Alpha by 4 alpha. Right. So when u by t becomes 4 alpha, beyond this value of u, this term dominates and the electron motion becomes suppressed. Okay. So there, at that value of u, I should get a transition from a metallic system to an insulating system. Very sort of naively looking at it. So in fact, I'll draw this for you. So this is energy and this is epsilon on these sides, which we have set equal to 0. And what I'm plotting on this direction, in this direction is u over t. And this is the point where u by t equal to 4 alpha. So in this part, so you'll find this figure in the book. You should have so in the left part, the electrons are itinerant, they can move around easily. And then the transition happens at u by t equal to 4 alpha, and beyond which they become localized on individual sites because double occupancy costs energy. It doesn't help. Before this term dominates, and this term you can view it as like electrons simply delocalized, that lowers their kinetic energy. Here it lowers their band energy. Although strictly speaking, band energy contains both kinetic energy of electrons and their interactions with the nuclei. That has all been clubbed into this. But the way these things appear, when electrons are mobile, this term is lowered, so that helps. But once u goes beyond a certain value, the double occupancy energy cost becomes prohibitive. So you have a metal to an insulator transition. Okay. So this transition, this metal insulator transition is not due to a half-filled band in the sense of an electron, an independent electron picture. Something else is happening. This is due to interaction localizing all electrons collectively. So this is a correlation effect. This is not due to a half-filled band. And this transition is called the Mott transition. So this is what happens here is called the Mott transition. And the insulators you get this way are called Mott insulators. Cobalt oxide happens to be a Mott insulator. Okay, so that's the first piece that we learned when we sort of asked the question that what was it that we were missing when we tried to understand cobalt oxide. Well, it's a Mott insulator, fine. So we have understood why it's an insulator. If it has a large U, then it may become an insulator, and actually that's what happens here. As I said, and here of course you have to take my word for it, that in this ionic compounds of 3D transition metals, this U becomes very important. But we still haven't understood why it is an antiferromagnet. That's the second part that we need to understand. Some general statements before that. before we go to the antiferromagnet thing. So what we see is that what matters in this kind of Hubbard model is the value of U over T. Okay? So U over T determines whether a system would be metallic or insulating, and so sometimes it's given in terms of U by T, sometimes it's given in terms of U by W, where W is the bandwidth. Bandwidth, just to remind you, we have discussed this, is the difference between the lowest energy in a band and the maximum energy in a band. The band maximum minus band minimum is called the bandwidth. So obviously it would be something proportional to T. So instead of writing it in terms of U over T, one often views it in terms of U over W, but W is some constant times T depending on what sort of lattice you have, in what dimension, and so on. But otherwise the concept remains the same. Okay, and so a Hubbard model, one band Hubbard model at half filling is an insulator. Some quick statements about what happens when we move away from half filling. So if n were to be less than 1, what do you expect? Monojit, what would you expect for n less than 1, the small n less than 1, when you have less than 1 electron per site?
It will be a metal.
That will be a metal. And what happens when n is greater than 1, but of course less than 2?
It will be it will tend to be an insulator.
Why is that? I mean, what is your argument?
More electron means there will be high interaction. So if the density increases,
yeah, the density increases. So filling is more than half. So small n is greater than 1. How would you put those electrons? You put 1 electron per site, okay? So that takes up L electrons, but then you have a few more than L. So they will go to some other site. So no matter what you do, some sites will be doubly occupied, right?
yeah.
Now, once you have certain number of sites doubly occupied, but not all sites doubly occupied, these electrons can easily move around because it's not going to cost any additional energy, because whatever additional energy would cost, you had to pay that anyway because the number of electrons is more than L. So for these electrons in excess of capital L, they can move around without any additional cost of energy. Rather, they can lower their kinetic energy by moving around. So earlier, less than half filling, the physics was happening around the energy equal to 0 sort of level. Here, the physics is happening around the energy equal to U level value. Just think about it, okay? So earlier, you started with an empty lattice and then you put a certain number of electrons which were less than the number of sites you had. So some of them could, they could move around without, completely avoiding double occupancy because there were empty sites available. Now you have more than 1 electron per site. So you had to put 1 electron per site. You are left with some more electrons. So you put them. So anyway, you have some double occupancy. And so your energy, even if they don't move around, is something times U.
Sir?
Now, after this, if the electrons move around, they lower their kinetic energy. With respect to that, some constant times U value.
Sir?
Yes.
That should not even cost the energy, right? Because if we have n sites and let's say n plus 1 electron,
Right.
then a single site is doubly occupied.
Right.
Now, when that electron moves,
Right.
the other side is doubly occupied.
Right.
So, yeah, so the energy exchange is like minus u and plus u. That cancels out.
Yeah, exactly. So that doesn't cost you any energy of the order of U. So on the U scale, it doesn't cost any energy. Rather, it lowers the energy because the electrons are hopping around. So you gain band energy. So therefore, that system would also be a metal. In fact, one can make these things formal. There is a perfect electron hole symmetry in the model, in the Hubbard model. We'll not get into these aspects. So there is a electron hole symmetry. So anything less than, okay, so you are at the half filling. So certain value below half filling and certain value above half filling will give you exactly same physics, same behavior. In one case, you can think of these as holes, the other case electrons. It's exactly in the electron hole picture that we had discussed earlier. Anyway, that's not, I just wanted to give an idea that, if it is less than half filling, you should get a metal. If it's more than half filling, you should also get a metal. And just to be, familiar with the idea. But I don't want to spend more time on this.
If we ask about the relative conductivity in these two cases, I mean, less than half filled and more than half filled, what will
No relative conductivity. I did not ask about relative conductivity. I did not ask about any quantitative answer. I was asking about the qualitative answer. That do you expect it to be metallic, that is conducting, or insulating? Okay.
Okay.
Okay, so let's get back to the small n equal to 1 case. Is it an uninteresting insulator? Well, it's an insulator. We know so many insulators. Okay, I mean, if we forget about the distinction between semiconductors and insulators, there are so many materials that we know of that are insulators. Silicon is an insulator. Germanium is an insulator. Sodium chloride is an insulator. All these, ionic compounds are typically insulators. Hexagonal boron nitride is an insulator. So electronically, nothing much interesting is happening there. Now, is this insulator, is this Mott insulator, something similar? Let us, to understand that, let us take the idea that U is finite more seriously. So U is not infinite. What we are saying is that U is finite. So if U is finite and say one electron hops from one side to the next side, it costs energy, of course. But it doesn't cost infinite amount of energy. So that is not completely suppressed. In fact, I mean, one can make it formal at various levels. But what I would like to do is to sort of refer you back to our discussion of this ionic configurations of the H2 molecule. Remember that. What we had found is that if we allow these configurations, if we allow, and we argued why that should be allowed, because there are such matrix elements, hopping matrix elements. So here also we have hopping matrix elements. T is non-zero for nearest neighbors. So if such configurations are allowed, it actually lowers your energy. So the way one views that is the following. So suppose I have these two electrons here to start with. This electron hops there and hops back. So it's a T squared process, okay? One T for hopping from here to here and one T from hopping back. So this is, so when it hops here, that of course gives you a high energy configuration. But that's an excited state of the system. But then you can ask that if I consider these such hopping processes within the second order perturbation theory, what is the what we get? What is the change in energy? It turns out, if you want, you can sort of work it out. It's not very difficult. But within second order perturbation theory, I'll just give you the energy numerator and denominator without actually evaluating the expectation value of the Hawking operator. So there are two processes. So you get a t squared in the numerator, and then in the second order perturbation, you get an energy denominator, which is sort of the difference between the ground state and the excited state you are considering. So when two electrons are on the same side, you have a U. So you would actually gain energy of the order of t squared over U when you allow such hopping processes. So these are called, this is just a technical name that is used in this business, but idea is same as like allowing ionic configurations, allowing these hoppings and so on. So, so the electrons are not hopping around all over the crystal, but nearest neighbor hoppings are allowed. And if you allow that and treat those effects within perturbation, second order perturbation, you actually gain energy of the order of t squared over U. There are factors, but the factors are not so important. So then what does that mean? So this is like our kinetic exchange, right? We discussed kinetic exchange in the context of H2 earlier, but now we have put it on the model. So this is kinetic exchange of the Hubbard model. And that, but the important point to realize is that for that process to happen, for this electron to come here and go back, these two must have opposite spin. If they have the same spin, it cannot come here. Pauli exclusion principle will prohibit that. So only if this is up and this is down, this process is allowed. So this kinetic exchange enforces or gives rise to an antiferromagnetic exchange between neighboring sides, spins on neighboring sides. So what is the net understanding then? Hubbard model. So one band at half filling in this model, kinetic exchange gives antiferromagnetic coupling or between spins on neighboring sides. So that explains why materials like cobalt oxide and quite often these Mott insulators turn out to be antiferromagnets. And cobalt oxide is an antiferromagnet. Okay, so two things happening here: metal insulator transition because of electron correlations and an associated magnetic ground state. So magnetism is not some, standalone phenomenon. It's a result of electron correlation effects. All right. So, any questions at this point?
Sir, this means that if some part of the system is anti-ferromagnet, then this effect will propagate and it will make the entire system anti-ferromagnet.
No, see, for us, it's a homogeneous system in the sense. Apart from being on a lattice, this is a homogeneous system. So whatever happens at one place, the same physics happens at every other place. So there are no
Okay, okay,
separate regions, so to say.
okay, sir.
Okay, so this justifies Heisenberg kind of model. So then what I can do is, if electron propagations where I really have to worry about states that are at energy u relative to this ground state, are completely discounted because u is large enough, but such virtual hopping processes are allowed that gives rise to an antiferromagnetic coupling between the spins on neighboring sites. I can forget about the interacting electron physics on the lattice and just focus on the physics of these spins, okay, and describe that by a Hamiltonian, which we write so. Important point to remember is that what we are studying through these models, these kind of models, is the low energy physics happening at this energy scale around the ground state of this half-filled one-band Hubbard model. We are not, through these models, we cannot study physics that's happening at energy scale U. Right. And we have seen that kinetic exchange in this particular case gives rise to an antiferromagnetic coupling. Okay, the two spins would like to be opposite to each other. But again, I warn you here that this is a very simplistic picture. We'll soon see when we get to the actual discussion of antiferromagnetic Heisenberg model that this up-down idea is a little sort of inaccurate, I should say. Anyway, so we have this kind of spin models, and these spin models are called Heisenberg models. And we have a justification as to why we can get an antiferromagnetic Heisenberg model. Next thing we ask is, but then there are ferromagnets, okay? And we have seen that because of exchange between orthogonal orbitals, one can have ferromagnetic coupling or non-orthogonal coupling or non-orthogonal orbitals. Depending on the nature of the overlap and so on, one can have direct coupling, that is direct exchange, that is ferromagnet. So at least we have one justification where ferromagnetic coupling can appear. But if we ask the question, can one have ferromagnetic coupling in this sort of a Hubbard model? Is it possible? So that I have nearest neighbor ferromagnetic coupling between spins. Turns out that not in one band Hubbard model, but if you extend the Hubbard model, these are called extended Hubbard model. So I'll just discuss one situation where you can have ferromagnetic kinetic exchange. So that's the sort of interesting part. So far, we have seen kinetic exchange to be antiferromagnetic type. I'll discuss one situation where the kinetic exchange can be ferromagnetic. And there's a reason why I do that, because in the process, we learn about possibility of some new physics, okay, which is another example or another consequence of electron correlations. So, are you all fine up to this part? Then we'll move on to the next thing. Okay, so I extend the Hubbard model and I consider a situation where
have two orbitals per side, okay, phi A and phi B, but I have one electron per side, which can be either on orbital phi A or orbital phi B. So if we ignore the electron-electron interactions first, I mean, let us write the different sort of types of terms that we'll have in the Hamiltonian system. So, which is of course, the Hamiltonian is of course independent of how many electrons we have. So Hermitian conjugate of that. The other hopping term just happens to be the Hermitian conjugate of that. Minus B. Okay, so these are the two types of hopping terms that we have. Notice the assumption is that hopping happens only between phi A orbitals of two sides or phi B orbitals of two sides. So this is phi B and TB and this is TK. There is no AB hopping. And one can justify that based on kind of structures that we have in real materials. It is easy to see that these would be dominant. Then putting two electrons on the same orbital, of course, costs energy, and there can be three different situations. Phi A can have two electrons up and down, so that costs an energy UA. Similarly, there can be two electrons on phi B, so that costs an energy UB. And I can have a situation where phi A has one electron, which can be, up or down, and that costs an energy UA. In addition, when two electrons occupy two orbitals on the same site, there's an exchange energy gain. It's the sort of ferromagnetic exchange between orthogonal orbitals. It's the Hund's first rule. So we call that exchange we call this intra-site exchange, as we write that as 2J. All right, so so that is that is not the full Hamiltonian. What did I write it? That's the hopping part of it. And here I will write the interaction part of it. So no dagger here. JB up, JB down. Plus So let me tell you what 1, 2 I'm talking about. So now, with this, what I'm considering for simplicity is a two-side problem. Side 1, side 2, just to understand what sort of exchange I'll get. So this is how I would write a general hopping term on a lattice, but now I'm specializing to a particular situation where I just consider two sides. And on these two sides, these are the interaction terms for two electrons sitting on A. It could be side 1 or 2. Two electrons sitting on B. It could be side 1 or 2. Two electrons sitting on side A and B. Again, it could be side 1 or 2. And then we could have two electrons sitting on two different orbitals, which would give me this exchange contribution, which can be written as this is J, and the reason for writing this term in this way is that you can easily check that if you consider two situations where the two spins are pointing up, that is both SZs are half, the other situation where one is half and one is minus half, the energy difference between those two situations would be G. So this is the sort of different parts of the Hamiltonian. There will be a spin flip term also, but let's not worry about that. But just for the sake of completeness, let me tell you that there will be some spin flip terms. Let's forget about that. Okay. So now, what are the possible situations? So there can be several singlets, triplets, etc. because I have two orbitals per side and one electron per side. I can put them in various ways. Rather than going through the entire discussion, I'll consider, so to start with, I have one electron per side, okay? So in that, I'll consider two situations, a singlet and triplet, and try to argue that which one has a lower energy. So let me just get to those figures. Okay. So now, given two sides 1 and 2, I'll consider. So this is side 1. This is this. No. All right. So I can have a singlet in which I have one here. And then I can have virtual hopping situations where this comes here, and then they go back to this state. So when you consider such processes, it's a usual thing that we just saw. I mean, I'm completely forgetting about this orbital. Okay, everything is happening within the A orbital on the two sides. So this process would lower the energy by something which goes as, there's a factor of 4 here, but apart from that, so the energy will be lowered by this amount, T squared over UA, 4T squared over UA. So that's one possible scenario. Nothing is happening on the B sides. And similarly, one can have, so this is a singlet, we call that A singlet. So, A singlet has energy, which is, don't worry about where the 4 comes from. I mean, I can erase, I mean, I can delete, so skip that as well. That's not the main part of the argument, it's the energy scales that what we are arguing about. Similarly, I can have a B singlet, where these 2 electrons would be in these 2 orbitals, and they will exactly go, follow the same, go through the same virtual hopping process. So this will have energy, which is this. If I have an A triplet, which I draw like this, then the hopping is strictly prohibited because this cannot come here because of Pauli exclusion principle. So if I write that as A triplet, that is equal to the energy of B triplet, and that should be 0. So this is the 0 energy situation. These situations, a lower energy by this amount of this amount. Sorry, there has to be an A, there has to be a B by this amount, whereas this triplet is at 0. But then I can have an AB triplet. So I can have, I can have this situation. I can have a triplet, but an AB triplet. From there, what can I have as intermediate state? I can have this and this. And then I can have that, my original state. Or I could also have this is also an AB triplet. Okay. Now, if I just focus on this part, what is the energy of this process? This is 0, and this involves a hopping TA, and when TA gets back, so another TA, and the intermediate state energy is UAB minus J because, sorry, I talked about triplet, not a singlet. So this is UAB minus J because 2 upspin electrons are 2 different orbitals on the same side. So this term then contributes an energy G. Is it G or should it be 2J? It should actually be, no, it's J. Fine. So this thing, so this, just looking at this, I'll get energy which is minus T squared over UAB minus J. Similarly, I could have the B of this thing hopping. So this could come here and get back here. So by that, I will get minus TB squared over TB minus J. But then I can have this thing going here as here and this getting back. So this involves a TA hopping and a TB hopping. I could have the other way around. The intermediate state could have been this and this TB and then TA. So there are two TA-TB processes possible, one TA squared possible, one TB squared possible, and in each case the energy of the excited state which comes in the denominator is UAB minus J. So in general, I mean this sort of an AB triplet, if I call that AB triplet, its energy is going to be this. Now compared to this obviously is lower because you have more processes here and the energy denominator is lower here because the assumption here is that in this sort of situations, TAs are smaller compared to UAB and G. So this will give you a lower energy denominator, so this energy will be higher. So this is the lowest energy state. That's the argument. Now, this is all the sort of hand-waving plausibility argument. There's nothing rigorous about. So don't try to think that there's, I'm proving something rigorously. I'm not. But being able to make this sort of arguments is also important. So this argument shows that this triplet, which we call AB triplet, should be the lowest energy state. Now, AB triplet is ferromagnetic. So here is a situation where I have two-band Hubbard model, two orbital per site Hubbard model with one electron per site. That gives rise to a ferromagnetic kinetic exchange. So I get here a ferromagnetic kinetic exchange. So not in the one-band Hubbard model, but in the two-band Hubbard model, I get a ferromagnetic kinetic exchange. But look, something else has come out of this. For me to have this state, this orbital, phi A has to be occupied by the electron here and phi B has to be occupied by the electron there. Now, if I translate this to the lattice situation, so again, let me draw the lattice and the generic square lattice in 2D. And suppose here I have the phi A occupied. Now, for the system to gain this energy because of this kinetic exchange, its nearest, so this can hop to 4 of its nearest neighbors. These sides have to be occupied, I mean the phi B's have to be occupied here. So that's the important understanding. So on alternate sides, phi A and phi B orbitals will be occupied. This situation is called an orbital order. The orbitals are ordered in the sense that on alternate sides, alternate orbitals are occupied by electrons. So that is again a consequence of electron-electron interaction. And of course, Pauli exclusion principle. And along with that, out comes a ferromagnetic kinetic exchange. And there are transition metal compounds which show such orbital order. The lanthanum manganese, for example, LA, NO3. We will not get into the details of any of these because we don't really understand these
specific materials unless you really understand their crystal structure and so on. But the essential physics is that of what we discussed here, LNMNO3, and this sort of ferromagnetic kinetic exchange. So yeah, so another compound would be A2C. This is another example of the ferromagnetic exchange. And for AFM, cobalt oxide was one I told you. Then this is another famous example, La2C2O4. This is a very, very well studied compound because I don't know how many of you are familiar with that. Have you heard of the term high temperature superconductors? Yes? No, Harshit? Harshit, can you hear me?
Yes, sir. I have heard about this.
Yeah, do you have any idea what are the materials which...
I don't know of the materials, but like I once attended a talk in my university when I was undergrad. So
Okay.
Yttrium, barium, copper oxide, I guess, is.
yeah, something like that.
Yeah, there's actually a whole bunch of materials. The first one which showed what is or what was at that time called high temperature superconductors was this lanthanum copper oxide. When doped with strontium at beyond a certain doping level, it showed superconductivity, which was sort of a complete surprise. But it turns out that, just leaving aside the superconductivity part, the parent material itself was quite interesting because, again, the band structure, band theory would tell you that it should be a metal. It turns out to be an antiferromagnetic insulator. And then, of course, it was realized that it's an antiferromagnetic insulator because of correlation effects. And what you can describe this material, the essential part of the material which is responsible for magnetism, using a Hubbard model. So it's the same physics that we discussed here earlier in the context of cobalt oxide. So similar physics is at play in La2CuO4, which makes this material an antiferromagnetic insulator. And then, of course, it becomes a superconductor and so on. Okay, so with these, what I hope I have been able to do is to give you an idea that magnetism is sort of an emergent phenomenon which emerges because of electron correlation effects and the fact that electrons are fermions. But it's an emergent phenomenon along with several other possibilities, one of which is metal insulator transition, which we call MOT transition, and orbital ordering here, for example. Now, if you bring in coupling of these electrons with lattice degrees of freedom, that increases the complexity of the problem further, but that's not something we want to get into. So what I at least tried to do here is to give you an elaborate justification as to why one at all should study Heisenberg models. I mean, one can write down the Heisenberg models and go on to discuss technicalities of it, but without any physical idea sort of why that one should at all study that model, I didn't find it to be sort of very motivating. So that's why I went into this discussion. And now we'll get back to our discussion of the Heisenberg model. Not get back, but sort of get into the discussion of Heisenberg model. Okay, so any other questions you have at this point?
Sir, I don't have a question from this, but my question was related to conductivity. I mean, we used initially in the first few lectures we derived the conductivity relation like J equals sigma E using Drude theory,
Right.
and that came out to be Ne square tau by m,
Right.
and this tau was what do we call it? The average time of collision when we saw electrons as colliding with a lattice and also electron-electron interactions. But uh,
We
but
did not really talk about electrons. I mean, okay, go ahead, then I'll.
yeah. But when we were doing quantum theory, like the semi-classical theory, and we sort of derived the same result using quantum theory, the semi-classical theory, and we got the same result, Ne square tau by m, if the lattice was sort of isotropic. I mean, in all the three directions, the components of m are same, the m tensor. But here we already said that the electrons interaction with ion is already taken into account by these block states. So this tau is only due to electron-electron interactions.
Okay.
So although we are getting the same result, I mean expression-wise, the tau is different.
Just to clarify, the tau is relaxation time, right?
Right.
Isn't that just the collision time, like average time of collision?
Yeah, that is the same, right?
Well, that's not as significant. I mean, that's not an important distinction. I mean, so tau is defined, I think, best thought of in the sense that the probability that an electron undergoes a collision within the time interval dt is dt over tau. But that's not the important point. The important point to realize is that, and we did not go into further details of that discussion, is that, I mean, see, tau is the sort of weak link of those theories. Definitely the Drude theory, and also even in the semi-classical theory. So, what exactly tau is not really very clearly defined. What you assume is that there are some collision processes in the solid, and then in a sort of phenomenological sense, in a statistical sense, you define this quantity tau. If you are ever asked to calculate tau from first principles, that's when you have to really come up with an understanding or a clear sort of statement about what is causing this tau, which is not done neither in Drude theory nor in the semi-classical theory. So that is something you have to sort of accept it at that level. But if you push it a little further, yet Drude theory, it doesn't talk about electron-electron interactions. It does talk about electrons colliding with ions. So, and then it sort of washes its hands off and says, oh, that causes those collisions. But when you come to band theory, we know that that cannot cause the collision. But there is something else. Now, we also know at that stage that no sort of crystal is perfect. Two reasons, and these are points I think I mentioned. Two reasons. One is that the ions vibrate. So the band structure that we calculated was for stationary ions, but any finite temperatures or even at zero temperature, because of the 0-point motion, the ions are not stationary. So that causes sort of deviation from a perfect crystalline order, number one. Number two, any real material is never 100% pure. You will have impurities, you will have missing atoms, you will have atoms sitting at wrong locations, and what are called dislocations, disclinations, blah, blah, blah. So all these things actually cause electron. I mean, electrons would scatter from one K state to another because of all these imperfections. So these are things that disturb this perfect crystalline order, and therefore you can have electron scattering.
I mean, I'm not going to the cause of electron scattering. I'm just saying that the definition we gave for relaxation time in both the theories are quite different.
No, what is the definition of the relaxation time in the semi-classical theory?
I mean, the analysis that we have done, we have said that, I mean, we didn't give any appropriate definition for
I think
tau
he's
and
saying that in the
Fermi.
block model, there is no like analogous collision happening. Like in the Drude model, we are simply considering electrons colliding with ions. But
Yeah, that
in
is
That
the
is
point
true.
I'm
Like,
emphasizing, that yes, electrons are so, it cannot be explained by electrons colliding with ions anymore, but there are always some imperfections in the solid which causes these collisions. Beyond this, even that theory, semi-classical theory, does not try to explain where tau sort of arises from. You have to just keep in mind that no solid is perfect, so therefore there are imperfections which cause these scattering events. And then take tau in sort of a phenomenological sense, that it's average time, etc. Then it's exactly the same. The origins have to be different, because in semi-classical theory you cannot pretend that electrons are undergoing collisions with atoms, because those effects have already been taken into account. So there has to be something else. Well, you say that, well, there are always imperfections in the solid. It's never perfectly crystalline. Beyond that, you don't say anything. You just go to your semi-classical equations of motion. So you don't try to specify tau beyond that level. So that is something you have to sort of appreciate and accept.
okay.
Yeah. Okay.
Sir, I have a question.
Yes.
Yeah, sir, in Hubbard model, when we have this Hamiltonian, we have the kinetic term is doesn't commuting with this on-site Coulomb interaction term. So we are applying here this approach, perturbative approach. So because we can't diagonalize this Hamiltonian, right?
Mm-hmm.
So again, when we are using this mapping to this the Heisenberg model, this is some sort of this. Are you using this diagonalizing approach for
No,
this?
no, 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 no. Nothing is diagonalized up to this point. What we have done is we have just looked at identified the low energy processes in the model. Okay, high energy processes will be ones in which the electrons actually hop around the entire lattice, and those will cost you energy U. Here, one is talking about what is in this field is called, these are virtual processes. So the electron is not really hopping and spending considerable time on the next lattice. But if you just allow this, so if the sort of, because you have hopping in your Hamiltonian, if you allow this one electron per side state to mix with doubly occupied states, that actually lowers your energy. So these virtual processes lowers your energy, and in the process, these virtual processes are allowed only when you have certain orientations of electron spins on the neighboring sides. So now if you think of, if I go back to my one orbital per side, okay, so one orbital per side, the Hilbert space at this one side is 4-dimensional, because I can have 0, I can have up, I can have down, or I can have up-down configurations of these orbitals. So this, and then when you have many sides, there are many possibilities. So what we have done in this case is we have reduced that discussion to a case of one electron per side, so which can be either up or down. So I have reduced this 4-dimensional Hilbert space to an effective 2-dimensional. I mean, I'm sort of looking at a subspace of that, up or down, which gives me the low energy physics of that model. And in that low energy physics actually involves interaction between spins on neighboring sites. So it is this low energy spin model, low energy effective spin model that I'm sort of studying now. So you have to understand that it gives some aspect of the physics of the full Hubbard model, but not all physics.
Okay.
Okay, what is the time? Okay, let me spend about 5 minutes on talking about the Heisenberg model, and then I'll close today. We'll take it up from here next time. So let us first look at the ferromagnetic Heisenberg model. So if this J happens to be less than 0, if it happens to be negative, then I have a ferromagnetic model, because then successive spins on neighboring sites would prefer to be aligned in the same direction. That will lower the energy. So the ground state of this model is already, it's exactly known. So there are no about the existence of long range order. So what is long range order? Briefly, I have a spin at some site I. And I have a spin at some site J, psi dot is J. I take average of that with over the entire system at some temperature. So it's the statistical average of quantities like this. Now, if this quantity happens to be sort of go to a finite value, as even when I and J are far apart, you say that the system has a long range order, very crudely. If it doesn't, if there is no long range order, then this thing, it's sort of similar to when we were discussing crystalline solids versus fluids. There we were talking a positional order, the correlation function, the density correlation function. Here one is talking about the spin correlation function. If such correlation functions die out, as soon as my I and J happen to be start becoming farther and farther apart, then you say there is no long range correlation. In fact, when there are no long range correlations, sometimes in many systems it would just die out exponentially with the distance. Then in some other unusual situations, you can have a power law correlation, and so on and so forth. But anyway, long range correlation, when psi dot st is finite, even when I and J are far apart. Okay, so the ground state is known. There is long range order, ferromagnetic long range order. So what is the ground state at t equal to 0? So let us see how to understand that. So in order to understand the ground state of the ferromagnetic Heisenberg model, let us look at a two-side problem. Okay. So if I have two sides I and j, then how should I write it? The total energy is just the sum over where Eij is the interaction between spins at two neighboring sides I and j. So how do I write I and j? Sorry, Eij. So Eij is so you can easily see that you will get, squares would cancel. You get 2 Si dot Sj from here. 2 cancels with these 2, so you get this. And there's a reason why we are writing it like this. Now, what we'll be talking about is spin S Heisenberg model. So, the spin at each side, of course, is the same, and it's spin S. So, we are not putting a special value of half or anything. General spin S Heisenberg model. So then, if it is spin S Heisenberg model, we know what these quantities are. So it would be so this is I squared and this J squared is plus 1. So plug in those values. So this can be written as then Eij. So this term is just this term, okay? And because j is negative, I just pulled out the minus sign and wrote mod of j. And same here, j is negative, so with these negative signs, it would give me a positive number. So I just wrote mod of j, and then I get two factors of s times s plus 1, so that cancels these two. So this is what I get. Now this is just a number. Given a spin S model, this is a constant quantity. Okay. Given a model, j is fixed, s is fixed. So this is just a C number. So what is, so when I try to minimize this, I have to minimize this. Now where is this term minimized? This contribution is minimized when Si plus Sj takes its maximum value. Now the maximum value when you add 2 spin S is twice S. So that will give me the minimum of Eij. So in that case, the minimum of Eij you get is, so basically what I'm saying is Eij is minimum. So one of this is twice this. Right. So if you plug in this value, what you get is so this is the same energy when this is, this energy is the same when you get, when you have
both these Z components are S. See, Z component of both the spins at I and J can have 2s plus 1 different values. But you get this value of the interaction energy when both are equal to S, just from this expression. So therefore, the sort of bond energy, if you wish to call it, pairwise interaction energy, is minimized when both have their Z components as S. Okay, that is what we understand. Now, so what is the ground state of this sort of spin lattice then? Spins on the lattice. Let me specify this. It's a ferromagnet when J is less than 0. So I can formally write the ground state of ferromagnetic Heisenberg model to be greater than equal to now let me explain this, and maybe I'll stop there today and then take it up from there. So what I'm saying is, I know how to minimize, or what spin configuration would minimize interaction of a particular pair of spins. Now I have, when I'm on a lattice, I have many such pair interactions. Okay, if I consider this one, this it interacts with these 4, this interacts with these 4, 1, 2, 3, 4, and so on. So there are many pair interactions. So, I know how to sort of minimize each one of these pair interactions. So the ground state energy will be equal to or greater than when I have configurations so that each pairwise interaction is minimized. Now, why do we have greater than sign here? There can be situations where you know how to minimize pair interactions, but when you have an extended arrangement of those, you do not know of any configuration how to sort of minimize that. I'll give you one example. So consider 3 sites and consider a situation where the spins can be either up or down. You could have, for example, spin half objects on a triangle. I'm not even saying triangular lattice. Just let us think of 3 vertices of the triangle. And suppose the interaction is antiferromagnetic. So this J is greater than 0. So that if this is up and this is down, the interaction is minimized. Now, if you look at this should be down to minimize interaction. If you look at this should be up to minimize. So which one should it be? Up or down? You cannot answer that question. Okay. And so this situation, this sort of situation, in fact, the ground state of this happens to be something more. You cannot, with up and down, you cannot minimize the energy. But if you confine yourself to the up and down configuration of the spins, the energy cannot be minimized. And these 2 situations would give you exactly the same energy. And this is called frustration. The third spin is frustrated. It doesn't know whether to be up or down. And then again, this is a widely seen phenomenon in correlated materials. But let's not get into that. So we'll take it up from here next time. And we'll see that for ferromagnet, there is no such complication. And for antiferromagnets also,
It depends on the kind of lattice you are on, whether you will have frustration or not. On a square lattice, there is no frustration. On a honeycomb lattice, there is no frustration, but on a triangular lattice, there is a frustration.